plan. We're going to be building a machine learning, a deep learning framework from scratch. Well, mostly from scratch because we're going to use a little math helper library called NumPy. This NumPy library includes some like nice to haves, like outer products, dot products, multiplications, and some activations that we don't have to write ourselves, which makes it super easy. So boy, we'll be doing that. We'll make that happen. This will be really hard. This is like a hard thing because we may or may not make it. So we'll see. Shyam, how's it going? Hey, Stephen, how are you? We're doing good. Happy Friday. We are going to be doing some deep learning from scratch using one. We're going to use one library, and here it is. One library. Import NumPy as NP. NumPy, NUMP, and this is just a math helper library. It helps us, and so that's what we're gonna do today. We're gonna try it. We're gonna try doing this without Copilot enabled. No AI help. Well, we might have to look up a few things just to get things going, but like during the back propagation section. So we'll see if we can make it work. I don't know. I don't know. I think this is gonna be really challenging, but let's see if we can do it. So this is a good opportunity to encapsulate and leverage some object-oriented programming, some lightweight object-oriented programming. So we want to a class, a layer, and this will be, let's see here. Then we have underscore init, and then I think it's self, something like that. We're going to have some variables in there. We're definitely going to have, we have a def in it. Here we go. We're gonna figure this out. It's gonna happen. I know. Okay. Self dot input will equal numpy or np dot array dot random. I might need some help on this exact function call here. And then we need to know what size it's going to be. What's the dimensions? What are the dimensions going to be? They're a little bit challenging, which is going to be building a deep learning framework from scratch. What are you doing today? Oh yeah, there we go. That's what we're doing today. We're going to try building a deep learning framework from scratch in Python, almost from scratch. We're going to use this NumPy library here. This NumPy library, because I don't want to have to do math. Okay, let's see here. Layer A, or how about this? We'll just do A equals layer, and then we'll just see if that works. Oh wait, it's going to require some inputs and outputs. Are you using OOP? I am because we're going to be using multiple of a kind of a thing. We could create another file and just call it, we can do a module, but it's going to have stateful information, right? It'll have stateful information. So we need to be, we'll just call this, WEI, weights. This is going to be the weights here. So we'll do the weights. All right, layer A. Is that going to work? Let's see if that works. We need to specify. Hey, Mohammed, welcome in. I know, Ashford, I know we're using OOP. It's something like I typically want to avoid, but guess what? There's going to be multiple of a thing. So it's going to be multiple, but we're not going to do any inheritance. There will be no inheritance. It's not necessary in this situation. So we're going to keep it simple as possible. We're going to keep it really simple. Okay. So input, we'll just do 4 and 4. So let's be 4 by 4. And then activation will be a lambda, we'll have to figure that out. We'll have to figure that out later. We'll figure that out later. OOP is good. I like organized stuff. It's pretty nice. It's organized. This is like a good use case for object-oriented programming. Here we go. All right, so we got 2 layers. Looking good. Oh wait, there's a problem. What is it like? Oh, it doesn't want. What do you mean? Hold on a second. Non-default arguments follows oh, yeah, we have to have a default. So we'll just say tan h. What about polymorphism? I know we're getting way too far ahead now, Ashford. No, we don't need. It's hardly ever do you need polymorphism. Like I've never, in all my years of software engineering, I've never really ever needed polymorphism. I'm going to be trying to do a deep learning framework from scratch. From scratch today, we're using Python, almost nearly from scratch. Let's get rid of the activation for now because we're not using it. But we will add it later. Let's see if that's still looking good here. Thank you for the likes, you guys. Random. Oh, see now we got to, so maybe it's just numpy.random like this? Maybe it's just numpy.random. Yeah, so many likes there. Appreciate it. Is that going to work? Because still no, wait, module object. Wait, hold on. What do you mean? Module object is not callable. Oh, wait. Yeah, it is. Hold on. All right. So, I need to figure out, so I'm going to enable Copilot really quick just to figure out what the syntax is. Hey, Espanol, welcome on in. welcome on in. We're going to be doing some deep learning today. Copilot enable. Just real quick, and we'll say numpy random. Wait, yeah, numpy. Oh, so we have to do it like this? Is that what we have to do? Okay, fine. There we go. There we go. All right, we'll do it like that. Is it happy now? Is it happy? Let's see if it's happy now. Let's see. Copilot disable. We're going to try it without the AI as much as possible, but maybe for like easy stuff like looking up docs. All right, there we go. So we got that. We're good to go now. We're good to go. Let's see if we can print it. Print a.w weights. Weights. Yeah, there we go. Let's see if that works. Are we going to print? Are we going to get data? We're going to get data. Okay, there we go. Now we've got the brain, you guys. We've got the brain. Yep, I missed the .rand. That's what I did. Random.rand. You got it, Christopher. You got it. You guys are knowing. For now, let's hard code the activation function and see some outputs. Yes, that's a good idea. So we'll hard code it. I like tan-h is one of my favorite. My tan-h. Tan-h is one of my favorite activations because it just does a really good job. It does a really good. It's not the cheapest one. It's not the most efficient one, but I really like tan-h. It's really my favorite one. We've got some layers. We got some weights, and then we need a forward function. We need a forward. So def forward, that will be self. There we go. And then we need a loop. We need a loop through it, you guys. Oh, actually, forward. We need the inputs. Inputs. There we go. We need the inputs. Best activation function is heavily dependent on task objective. You're totally right. You're totally right. It is. There are some, like the output activation is typically depending on what your output's going to be. What do you want to target, right? Usually it's going to be a 1 or a 0 for classification of some sort, which is what we're going to be doing today. We're going to try to do, maybe we'll do an XOR. Actually, you know what? I don't know if we'll make it. I don't know if we'll make it, you guys. This is a task on its own here. We get inputs, and I think we can do an @ sign, and then the self.weights. I think that return. Let's see if that works. Let's see, but we didn't activate it. That's not. Oh, so this is output, or we'll just say out equals, and we'll copy this over here. There we go. Comma bird. Let's go over here, and then we want the activation, right? We don't know what the activation is going to be yet. Some functions I know. Input equals hidden rel u sigmoid tan-h output softmax. Yeah, softmax is good if you have, if you're doing a classification, right? But if you're doing a binary classification, you obviously only need one output, or if you're trying to target between two different outputs, then yeah, softmax would work pretty good too. Depending. So when you're training though, you want to target one specific output depending, I guess if you have multiple assignments, like if you have, what is that called? When you're trying to assign some like attributes, right? You want the AI to detect attributes of whatever the input is. Then you're going to have multiple outputs that can all be on at the same time. And so softmax may or may not work well in that scenario because you're polluting some. Yeah, it depends. It all depends, right? Okay, activation has to be written by hand. Okay, maybe. No. The formula has to be expressed manually. Well, it can be. So if we want to do sigmoid, so I'm not gonna fully remember what the activation is for, because we also need the derivative as well when we're doing backpropagation. And even if we get that far, we're gonna try, you guys. We're gonna try. So what we're doing today, Manu, is we're trying to write here. Today, we are writing AI or I guess ML framework from scratch, or from scratch-ish, right? Because we're using NumPy. Because it's otherwise, thank you for the likes. Otherwise, you guys, I would have to write a whole bunch of for loops, and the code would get really busy on screen. And we don't need to write some for loops just to, loop through all the arrays on the screen. So you can see here on the other side of the screen, we've got some arrays over here. You can see what the arrays look like. So that's what we're. How do we do tan-h? So I just need to enable Copilot really quick. Copilot, just for some document. I know we're doing this from scratch, but I mean, just a few things makes, because otherwise I have to go to Google and Google it, and I don't want to enable. Here we go. We need tan-h activation. All right. Let's see here. Okay, it is numpy.tan-h. Okay, so that's all we have to do. This is all we have to do. Boom, boom, boom. There you go. Right there, like that. So we're doing a little bit of helps there. What we're doing right now, we've got some functions right here. We've got our init function right here, and then we've got a forward function. So let's do return self.activation out. There we go. There we go. So now we've got our forward, right? We've got our forward, but I do want to say self.output equals out. Here we go. Because we need to save this. We need to save the output for training purposes. When we're training the model, we want to save the output. I remember this. I remember this part. Here we go. All right, let's see if we get our code to run here. Is it going to run? Okay, so we've still got it running. It looks good. Okay, so we got our forward, and then let's try to do a forward. Let's do input. Let's do XOR. Let's do XOR. I think that's easier. Okay, let's do input data, or just say data. Here we go. Data will be numpy or np.array, and then we'll specify this from scratch here. What will this look like? You can also do dot using dot. Oh, with the dot np.dot. Okay, cool. Thank you. We might need to do that. It depends. I need to see what the output looks like when we do this. Here we go. So blur, 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 like this, comma, this, and then I think that's, so we're gonna have, we need 4. I think we need 4 here. 1 2 1 2. Is that right? Is that, my brain can't see it? Where is it? Oh, because there we go. And then we go here. We're creating a data set. We're creating a data set. This is I would call this X. We'll call this X and Y, which basically just means input and expected outputs. That's all it is. So this is training input data. Okay, and so the answer is, and we go over here, copy paste that, and make this a Y. And the output only needs to be, we only need 1 on the output. So we'll kind of do it like this here. I've got an idea. There we go, like that. Something like that. And we can go bam, bow, and bow. There we go. And so what the answer is, in XOR, both the values need to be the same. So this is 1 here, and then this will be 0, 0, and 1. So I think that's what XOR is, right? I can't. Oh, wait. Someone's got. Wait. 0 0 equals 0. Oh, it's the opposite. It's the opposite. 0 1 equals 1. Okay, let's switch it up here. So we've got our X and we've got our Y. So we should be able to do a forward. Forward with our A. Let's see if we can do forward with A. Also, we don't have any. We don't have a bias, and I don't know if we'll have time to do a bias, but I think we can do it like that. Let's just put this over here like this. We probably won't use it, but we'll have it ready. We'll have it ready to go. We'll have a bias. Boom, bias. There you go. I see multi-functions. I am confused. I cannot understand. Multi-functions? Multi-functions? What do you mean multi-functions? There's only like there's 2 methods here. We've got an initialization method and a forward method. All right, so out equals inputs dot weights. Oh, wait, no, inputs is the right dimension. Are we talking about matmulp input op 1 has a mismatch in its core dimensions. Okay, so our weights, let's see, X, let's print out, let's do this, print X, and then print A dot weights. Let's see what that goes. Let's see, and we'll highlight that, close that off. Okay, might have a transpose matrix. It is. I think that's what we've got to check out. Okay, so because of 4 and 4. Okay, so we've got a 2 by 4. So we need the input layer to match. So A input equals 2, comma output equals 4. I think it's that. I think we have to do that. You guys. I think we have to do that. But first, layer object has attribute weights. Has no attribute. WEIGO /WEIGT. Where's that? Oh, all right. W. There we go. I gotta spell things correctly, you guys. Gotta spell things correctly. All right. We fixed it because of input output, and we have layer. We'll do this. We'll just copy and paste so we know, so we can see it. We could also create a model, and then so layer B, and then let's do C, and the C will be output. And we'll do 1. Here we go. All right, so this is our model. This is our model here. But we also need to specify a output. What should it be? It should be sigmoid, I think. So we've got our feed forward, and let's see if we can actually get it to feed forward now. Let's try it. Let's try to do feed forward. Is it going to work? Is it going to work? It feed forward. Look at that. But hold on, I see a problem. Oh no, we got zeros, a whole bunch of zeros. Okay, that's actually fine. That's actually fine because that's expected because we're multiplying these zeros with the initial zeros. So here, check it out. All right, so this works. We did it correctly, you guys. Our outer product is working correctly. And it has an activation, and it's working. We did it, you guys. This is so cool. Okay. Okay, now that we did that, what's next? What do we do next? Okay, so we have to propagate that data forward. We have to propagate the data forward with each of these layers. Let's at least try to do that. So, out, we'll just do a out. We go a. Let's do a out like that. I think it's front end of an AI, what it looks like, and especially in a deep learning AI. Well, I guess it's nearly deep because we got 3 layers, so I think that's pretty deep, don't you? I mean, we could go more, but I think 3 is enough for now. 3 is enough, and so you can see here, expected input size is 2. And then the output size is 4. So we've got 4 dimensions. And you can see that's because we're expecting 2 variables to be the input. But our batch size, here, let me pipe this over here so we can see better. Our batch size is 4. So you can see we've got an array of element of 4, right? So you got 4 elements in there. That's a batch size of 4. And each of these elements in that array is 1 training sample, essentially, or 1 input at that point. So what we've done is we feed forwarded a batch size of 4, and we got the output here on the screen so you can see what the results are. Now, it's random data. It's random. And so what we have to do next is train the model, and that's the hard part. That's the hard part, you guys. So we're going to need to implement some mean squared error. We'll have to do stochastic gradient descent to do the training, and we'll have to create a loop for that. And then we have to do back propagation, and then we have to optimize. Try this out. All right, so now that we've got the output, what we can do is we need to put this into like, what do you call it? Let's see here. Print that out. This needs to go like in a for loop for training purposes. So this is that. We do need a backward propagation. So this is the tricky part. Def backward, and then we have self, and then we have I guess the output or I guess the previous value. I don't know what to call this. I don't even know what to call this data. We'll just use data. There we go. Data. That's what it's called. We'll be generic. Can you use a CSV file as training data set in NumPy arrays? You're totally right. You can. You can't. All you have to do is import the data, and you just want to make it match it however you want. Match it however you want. So like this is essentially our spreadsheet right here. If you can see on the screen, this part, this is our spreadsheet data. But then we've separated it into input and output data. So we've got our input data, which is 2 variables, right? You got 2 datas, 2 variables to your input, and this is a batch size of 4. So it's essentially 4 rows and 2 columns. It's a 4-row, 2-column array right here. And that is basically our spreadsheet. But then you also have your answers, which is right here. So this is your output data, which is what the data is we're going to train on. This is the target data. This is the target. What you call the target, the expected output. This out. All right, so we've done our feed forward, but now we are going to have to do. So let's see. Let's specify some epochs. Let's do like 100 epochs. No, yeah, 100 epochs is good. Let's try that. So we'll do a for loop. How do we do for I in range? Do X range? Oh, range. I'm thinking Python too. We'll go epoch. Let's try that. There we go. So print. We'll go f epoch, and then we'll go I like that. Epoch I. Okay, there we go. And then we're building an AI or deep learning from scratch. So we're doing today, we are writing ML framework from scratch for the most part. We're importing a couple of libraries. So should the for loop be in a fit function? That's basically what this is. This is the training. This is the fit. Or like a dot train or a dot fit. Right? Because you've got these different You've got these different methods that are like that. That's basically what that is. So we're going to try to do that. We're not there yet. We don't have it fully yet, but you're totally right. Hey, MD, how's it going? How's it going? We're doing the AI. We're trying, but we need a backward, let's see, pass. Here we go. Let's see. We do need to do back propagation, which I forgot how to do, actually. Don't need to do that. I guess we could, but we don't need it to be, the optimization function could be outside of the layer. Outside of the layer, you guys, because we optimize each of them. And then we need to do it backward here. So basically we need to do the opposite. How do we do backward? Oh, because we have the output. Oh, got it. Okay, so we have the output, self.output. Okay. We're going to figure this out. Hey, why are we changing the activation of the last layer? We have to. I mean, it's better because the tanh has -1 and a +1. But our training data is saying that it's going to be 0 and 1. So we want something that's going to activate within that range. So tanh will activate between, so tanh equals basically -1 to +1, right? So that's tanh. But we need something that activates like sigmoid between 0 to 1, something like that. So that's why we need to change that. That's why we need to change that, because it's like that. We don't have to. So you know what? You're right. Let's keep things simple for now. And not. Although I really do want math. So how do you do round? How do you do rounding in NumPy? Today we're writing machine learning from scratch. Is what we're doing. ML from scratch. That's what we're doing. We're going to try the best we can. We're going to see if we can make it work. We have to pull it from memory the best we can. But let's see here. We'll keep things simple for now. We could also do that as well. We could absolutely also do that for the output layer. But for now, we'll just keep it simple. We'll just keep everything tanh, and then we need the derivative of tanh, right? So what is the derivative activation? NumPy tanh derivative. How do we do that? We need a little bit of documentation here. Tanh derivative. Oh, we have to write it ourselves? All right, that's no problem. We'll write it ourselves. No big deal, you guys. No big deal. All right, tanh derivative. Boom, we got it. All right, so we'll do this. Here we go. Over here. And then that will be lambda x : paste. There we go. Like that, just like that. Isn't that cool? Now we don't have to worry about our activation or our derivatives anymore. So self.derivative here. Oh, but we can't directly. Here's the deal. Because we're doing it like this, it's an array. So it's expecting the x is a single number, but we have to loop over it. X. So we could do something like map x, and then we say lambda n, maybe we can do like that. Map x. Yeah, map x. So this is the input data here. And then let's see if we can get, let's write this in a function. Let's make it a little bit easier. Let's make this a little bit easier for us. Here we go. So def tanh. This is an array. We'll just an array like that, right? We're figuring things out. And we go like this. We need the map over in. We'll say in here. And then what else? Is it? We don't need that anymore. We need this. So this is actually the tanh. This is the actual tanh algorithm, like that. All right, we're gonna figure this out. I promise we'll figure it out. We'll at least get close trying, you guys. We'll get close. All right, so we've got tanh, and then wait, is that actually how it goes? Is it actually like this? So is that the actual derivative? Because we don't want to re-tanh something that's already been tanh-ed, right? Is that right? We don't want to re-tanh something that's already been tanh-ed. Is that actually the answer? Is that really the answer? Efficient. I feel like we're missing something. I feel like we're missing something. Trying the best we can to create a machine learning from scratch, or deep learning, AI, essentially AI from scratch. It's been a couple years, but we're trying our best. So let's see if we can optimize back, and then we say optimize, and then but we need the weights. We need the weights, self.wei weights, and then the back propagation. How do we optimize? I know we've got a learning rate, so we got a learning rate. Hold on, learning rate. I know we need to multiply that. And then we need to have a derivative, or a delta, right? Delta. Oh, so we do need the delta part first. I forgot. So we've got the output, and then we need the delta. And then we need the delta, or delta. Thank you for the likes, you guys. Delta equals C underscore out minus Y, I think. I think that's it. I think that's the part we need, is those two things. All right. Does my program still run? Python ML. It does. It still runs. How is that possible? I don't understand. All right, cool. I'm glad it still runs, but we've got delta, print delta. Here we go. So what we need to do is we need to see how wrong the AI is. We need to see how wrong the AI is. So let's see if we get the print delta. Is that going to work? It is. It is working. Okay. And it's working really well. It's working very well. So we've got our output, we've got our delta. So we know we're good up to this point. We know we have good data up to this point. Here's why I know that. Because the answers are through the training data up here. So go up here. So we know that the answers are here, right? This is the actual answers. And then this is the result of the answer right here. This is what the AI model thinks is the answer. Obviously, it got it wrong. It got the first one right, perfect, but that's a given. It's a given because this is an XOR operator training model. And then the last one is wrong, but the middle two are also close enough. And so you can see that it's giving us a delta. So it says that the expected value for the last element is supposed to be 0, essentially. But as you can see, because you can see here, the expected of the last element is 0. But it's not, the model did not give us 0 output here. And so the delta, how wrong it is, how wrong the model is essentially 100% wrong for that last item. So this is the delta. So now that we have the delta, we can go a step further. Next step, we need to do the back propagation, and we need to optimize. So we're going to do that all in the same rate. All right, so we've got our, I guess we got our params. I guess our params is good to say, or weights, maybe we could say weights, and then our derivative back. So this is a back propagation. So we need the, how do we do this? How do we pass in our data, our next data? So I guess this would be the delta. The delta, is that what we need it to be? I think it needs to be I think that's the delta. I could be wrong, you guys. I could be wrong. It's been a while since I remember this, but we're gonna give it a try. We're gonna give it a try. All right. So backwards. So here we go. We'll do cout.back, and then we specify the delta like that. I think we do that. And so that is the. But then we need to capture the output here. So C back. Here we go. I think C back is good. C back works like that. And then we copy and paste that. And we do B and then A. Although we don't need to capture this last one, I don't think. B, A, like that, right? I think you guys, is this right? Or wait, no. Not C. I think we have to do this. There we go. Like that. There we go, you guys. We are writing a machine learning framework from scratch. We got pretty far. Just create an array which holds all the outputs, and then you can do it on backprop. Okay, cool. So I do have my output here. I'm saving my output on the forward. So each of the layers has its own own output section. Create an array which holds all the outputs. We could totally do that. So we don't necessarily have to do it like this. We do have the delta, right? And we can do a mean squared error. So this is the delta. And then I know there's like how do we do a mean squared error? I know we need to do that here, right here. This is where the mean squared error has to happen. What epoch and how does it help? Oh, what's epoch? Okay. So epoch is really simple term. It's just number of iterations on the full data set. That's all it is. It's just how many times are you going to train a model on the complete data set. So you can train a model on individual training samples. So say here, we've got 4 samples is what we have here. We've got 4 samples. You can see 4 samples of training data. Rate is just based on the delta, how far off the data is. You can apply a learning rate. So you times learning rate like that. And then you can use that to apply during back propagation to the weights to slowly adjust the model. So that way it tunes it. Okay, so that's actually a good point. So a batch can be just however, this is like a single batch. We're doing one batch, but we're doing 100% of the data is the batch in this case because it's a simple, we're keeping things simple today. We're keeping it simple, you guys. Nice. Recently been developing with TensorFlow neural networks. TensorFlow is a fantastic framework. It is excellent. It makes it easy, especially if you use Keras. Keras on TensorFlow is great. Keras on TensorFlow. I love it. Dabber coding. And don't forget the income gradient. For updating the weights is different than the income gradient to the next layer. You'll end with 2 gradients. Okay. Thank you for reminding me. We'll try the best we can. It's been so long since I've done this. It's been so long. It has been a while. So this is the hardest part, is the back propagation and the optimizations, the actual training phase. How frameworks came into being. We realized that we're repeating a lot of the code, and we needed to, and a lot of people are repeating a lot of the code. And so a framework becomes really valuable to place code that a lot of people are repeating. And so that makes it so they don't have to repeat the code anymore. They can just use the framework. It becomes a common worldwide pattern that everyone uses. And the framework should only cover the common pattern parts and then leave everything else up to the developer to add customization after. I think that's how you can answer how a framework comes into be. That's how a framework comes into be. But we're kind of building it a framework right now because this is a common pattern that everyone uses. I'm not sure how far we're going to get, guys. I'm not sure how far we get. But Dabber coding, you definitely know your stuff. You You absolutely know what's going on. So we've got our delta. Let me see here. So let's see. Delta. Okay. How do we? Okay. So we need our delta, we need our gradient, and we need to apply the gradient to the weights. So we've got our weights, we've got our back, or our data, and then we've got the delta. So we've got 3 variables. So we've got the delta, the weights, and the back. How do we do this? We don't need to do this yet, right? Do we do this part or the? I've completely forgotten how all this works. I need help. Why are we performing product of data with weights before performing derivative and back propagation? K7? Just denial of service? Is it sequence K? Denial of service? All right, how do we do this? I need to go look. I need to look this back up. I do need to look this back up to get the exact, but I feel like, okay, I think we need to do the derivative somewhere. We haven't done the derivative, and we only need to do this for the backward propagation backwards. See, I'm missing part. So we've got the delta, but don't we need a password that, see, this is where I need to start. I need elint delta all day. Is it elint delint? Hey, how's it going? Chidu. Hey, Ro, welcome on back. Happy to see you. MS-DOS, Microsoft denial of service. What is disk operating system, right? Disk operating system is what I think that stands for. Optimize function should subtract the delta from weights, right? Yeah, so we've got the part that I need to remember is how to go to the next phase. So we've got the delta here, but I just don't remember. I just don't remember at all. I don't remember this part. So we have the inputs from the outputs in previous, so we don't need to worry about that. But we do need to do backwards here. Optimize function. Yep. Okay. Oh, right. We only have 4 minutes left. I don't know how far I need to like look this up. I need to like do some looking up. Let's just, this is like the hardest possible thing. But we'll see here. Backseat print, C back. I don't know if that's going to work. C backwards. Are we returning anything? Return, and then let's see. Oh, we don't actually need to return. Do we? But we do. I know we have to do this. I know this has to happen. So that way we can pass it onward. But this is where I hit my wall. I'll need some help. We'll have to probably do part 2. We'll probably have to do part 2, you guys. But I think I need some help. All right, so let's zoom out here. Let's do update. So delta. I call it delta instead of error. So I called it delta instead of error, which is fine. We don't need to worry about that. And then we need to calculate the loss. Okay. So here we go. We can do this. We can do mean squared error like this. Let's do it. Let's calculate that. I like this. We need to do loss. All right. Loss like this, but we call it delta like that. And then, so we calculate delta. Here we go. Delta like that. I'm going to do forward like that. Forward. All right. So we're getting, what's your loss function? It's mean squared error. Oh, there it is right there. Here you go. Mean squared. Very simple mean squared error. And then, so we're not doing graphical processing unit training. We're not doing any special advanced hardware accelerated training. But you can sort of do a fused kernel, which I've done this before in the past, where you merge multiple tasks into a single step within the GPU layers, which makes it a lot faster. They use this strategy. It's called flash attention. It's called flash attention, but all it is they just merge multiple tasks into a single GPU step, such as like activation and the forward pass all in one. Like they do like that, bro. You know, every concept in CS. This is what we need to make sure we got right. All right, so our gradient is, so we're going to make a gradient for each of our layers, and then we're going to get the derivative. Okay, so derivative of the predicted output. Oh, okay. So like this. And then, so there's the output, but then this is the delta or the loss we're going to do. We do have to get going here. All right. But I just wanted to, so we don't need to worry about bias right now. We don't need to worry about bias. We don't need to worry about the bias yet. We're not using bias right now. We'll get to bias later. Output and the gradients. Oh, gradients. Equals directly. Oh, okay. So this is going to be used here. Okay. Just trying to understand some things, you guys. Just trying to figuring these things out. So there's a transposition that occurs here. Gradient of loss with respect to the output layer weights. Okay. I'm lost. I don't understand what you're using the loss function. Oh, as a loss function. So you can just it's actually really simple. It's just mean squared error, MSE. And this will work. I know this works because I've done this a few times. So with loss, maybe loss here. Do we want to do loss here? Is that what that is? Because that's the error. And then are we doing it with the error? So output prediction error, right? Okay. That gives us the gradient for the layer. So at least we should, and then we can return it if we want. We can return it, but we don't need to. So we'll just say backward that, and we'll just say c.gradient. All right, let's see if that works. Python AI, wait, ml.py. Okay. We have an error. Let's see if we can fix it really quick. And then this will be the very last thing that we do, and then we'll have to resume this. We'll have to resume this on Monday. We'll have to resume on Monday, you guys. That'll be the plan. We tried really hard. This is a hard mode stuff here. We're trying to do everything that's done in sort of the TensorFlow and inside of PyTorch. We're doing from scratch. Now, let's see if we can fix this one error. Layer object has no attribute derivative. All right, did I just misspell it? Oh, I never said it. You guys. Here we go. Derivative. Here we go. There we go. Is that fixed now? Is it all better? Is it happy? It is. It's happy. Check it out. Okay. So we did our back propagation. We've got our out, right? So we got our gradient there, our back propagation gradient. We made progress. We're making progress. 100%. You got it. 100%. Table DHCP kinda. 100%. Okay. So we've got our gradient, which is great. I'm actually kind of excited about that. So we've got our gradient. Perfect. And then I want to do one more. Let's go one step further, you guys. Let's go one step further. Reference. Okay. Hidden layer. So this is the next one. So, but I'm actually curious. Hold on a second. Wait a second. I know we need to do this. I know we have to do, wow, this is a lot here. This one line is crazy. And then we have to transposition X, which is the input. Oh, I forgot. Did we save the input? You guys? I don't think we did. We have the output. Self.input equals input. Inputs. Here we go. Okay, I forgot. We got to save that. So we got to save that. So we got self.out, and then we've got our inputs. So that way we can do back propagation. Okay. We got a layer, and then we did our initialization. We've got our activation and derivative. We do have a bias here, but we didn't use it. And then we have our forward propagation, which we did correctly. I know this part because the easiest part. We did this part and we did it perfectly. And then we have our forward pass with all the layers. And then we went through and then we started doing training. This is the training phase, but we don't have everything we need. We need to fix this part right here. We need to fix the backward propagation, gradient generation, and the training aspect, which is the optimize, right? The optimize is really just the training. This is just the training section. So that's what we'll do on Monday.